So we're seeing through types of electrophilic addition reactions, so reactions of alkenes. And in the last video, we did preparation, and then we did 3 reactions. So halohydrogenation, or hydrohalogenation, sorry, got it backwards. Halogenation, and then halohydrin formation. In this one, I'm going to add our 4th type, which is going to be hydration. So if we're hydrating, right, we've had a lot of water. So a hydration reaction is we're going to be adding water. And we're actually going to do this 3 different ways. So addition of H, OH, right? So on one side of our double bond, we're going to end up with an OH group. On the other side, we're going to end up with a hydrogen. So we're going to be producing an alcohol. So it produces alcohols. And then I'm just going to put water in parentheses here. The 3 different methods, sometimes it actually looks like we're adding water and sometimes it doesn't. So addition of water in quotes. So our first method for doing this, method A, is going to be acid catalyzed. So for this one, I'm going to use water and then sulfuric acid, H2SO4, and water. I just put them both on the arrow. I think on your reaction sheet I have water on top and sulfuric acid on the bottom. It could be the other way around. Remember, it doesn't necessarily mean anything where it is on the arrow. So I'm actually mixing this one up on purpose just so you don't kind of get stuck in that rut. I find that people are starting to do that, so I'm just mixing that one up a little bit. And we're going to end up with an OH group on here. If it was chiral, we would get both stereoisomers. So it is not stereospecific, right? We get both. It can add from either side. It is going to go through a carbocation rearrangement, which is how we get to that. Or sorry, it's going to go through a carbocation intermediate, which is how we get to both of those stereoisomers. So you do have to watch out for rearrangements. And then it also follows Markovnikov's rule. Notice how I put the hydroxyl group on the more substituted carbon. So we get our Markovnikov product. Again, the Markovnikov product has my hydroxyl group on the more substituted carbon. And then it is going to go through a carbocation intermediate. So we want to watch for rearrangements. Right, we're not always going to have them. We're only going to have them if it makes it more stable, but do watch out for that. So our mechanism. So I am going to use hydronium ions just like I have in the past when I've had a strong acid in water. So I know that H2SO4 plus water, right, gives me hydronium ions, right? The sulfuric acid is going to give a proton to water. Essentially, water is going to grab that proton if we were drawing arrows, and I have hydronium. So I'm going to do it that way. If you want to use sulfuric acid, that's fine. You will have to draw out a couple of those bonds, though, because you are going to need to show breaking a bond between a hydrogen and an oxygen. So my mechanism, since I'm using hydronium, my double bond electrons, right, my pi electrons are going to grab onto a proton and I'm going to break that bond. If you were using, let me draw it up here kind of small, right, if I was using this one, it's going to grab onto one of those protons. I do have 2 of those OH groups, it doesn't matter which one, and you're going to break that bond. So I now have a carbocation intermediate. I'm drawing the more stable one because I get Markovnikov's product. Just remember, just like we did with the hydrohalogenation one, we could also get this, right? This is the one on top is that's going to give me my major product. I have water floating around. Oops, wrong color. And it has its lone pairs, so it's going to grab onto that carbon. Right, that's my non-octet carbon. I have an empty p orbital that can accept those electrons. Since it's planar, it could add from the front or the back. So if this was chiral, that's how I would get those two stereoisomers. It is acid catalyzed, so remember if something is catalyzed, I need to regenerate that catalyst. So I'm going to have another water molecule, which was the conjugate base for my acid, come and grab onto a proton, and then don't forget the electrons between the proton and that oxygen go onto oxygen. If you would have used sulfuric acid instead of hydronium, your conjugate base would be this, and then that would go grab a proton and you would go back to your acid. So my product, again, OH. Remember, if chiral, we get both stereoisomers. Right? I could have that hydroxyl group coming out, or I could have it going back. Right? Planar. Right? It's sp2. So water can add from either side. And then getting lost in here is this guy. This would give me my minor product, right? Minor product. And I still have, planar intermediate, I would still get, if chiral, both stereoisomers, because my water can add from either side. So it just happens to be different regiochemistry, similar stereochemistry. So our second hydration method is called oxymercuration. And this one we're actually not going to do the mechanism for. I'm going to do part of it, but you're not going to have to reproduce it. So you don't actually need to know the mechanism for this one. I know that's a rarity. So don't need to know the mechanism, the entire mechanism. I am going to do part of it because it's easier to explain some of the stereochemistry if we do, but I'm not going to ask you to reproduce it on a test or a quiz. So this one, I'm going to start out with the same alkene. And then we're going to add mercury acetate in one step. Remember, if I have the 1 and 2, it's really important that you have those because we need to add them in separate steps. So mercury acetate. And then a second step, I'm going to add sodium borohydride, so NaBH4. I don't think I've used that before. OAC with a negative charge is an abbreviation for acetate. It's a really common organic abbreviation. Remember acetate. Sorry, that's kind of a mess. Let me try to draw it better. We'll just draw a skeletal structure. Right, is this from general chemistry, right? This would have been acetic acid, and if we got rid of the proton, we have this, which is acetate. So it was one of the polyatomic ions that you would have learned in 150, 151. In 152, it would have been the conjugate base of acetic acid, which is a pretty common weak acid, so you probably would have used that a lot. OAC is our abbreviation in organic. We just kind of get lazy and assume that you know what that means. Mercury here has a +2 charge, so I need 2 of those acetates for every 1 mercury plus 2. The O stands for oxygen, so it's capital. The A and the C actually stands for acetate. The A is capital, but the C is lowercase. Even though it's just an abbreviation, the capitalization that matters for whether or not it's correct. Okay, my product. So this one, I am going to get my Markovnikov's product, so I am going to put my hydroxyl group on the more substituted carbon. It's also regiospecific, it's also stereospecific, and I'm going to get the anti-stereochemistry. And I know you can't really see that with this because the other carbon that's in the double bond doesn't have, actually let's just put a methyl group, didn't have any groups on it. So I want that hydroxyl group and the hydrogen. And now remember we're adding water. So even though it doesn't look like we're adding water, that's what we're doing. So when I say anti, I'm saying this hydroxyl group and this hydrogen are going to be opposite. So because I have that hydroxyl group coming out, I would have my hydrogen going back, which means the hydroxyl group on this carbon, sorry, not the hydroxyl, the methyl group on that carbon is going to be going out. So if I would have left it how it was before, there'd be 2 hydrogen on that carbon and you couldn't really tell that stereochemistry. So basically this group and this group are going to be anti to each other. So stereospecific, it's anti, right? And by anti I mean the hydroxyl group and the hydrogen. And then it's also regiospecific. It follows Markovnikov's rule. So Markovnikov product. So my hydroxyl group goes on the more substituted carbon. By putting that extra methyl group on, I can't really show that part of it, but do know that it follows Markovnikov's rule. So you do want, if it's not equally substituted, the OH group on the more substituted carbon. Maybe we'll draw both of those just so you can have them both. So this one and then the original one before I redid it. I have this, and then again the one. So this is how, and this is how I have it on the reaction sheet. You can't see the stereochemistry, but you can see the regiochemistry. The one I did up here, right? You can see this the stereochemistry, but not the regiochemistry. So you get it both. This one I said we weren't going to do the entire mechanism, but I do want you to know that it goes through a cyclic intermediate. So again, the mechanism, you don't need to reproduce. Meaning I'm not going to ask you to draw it on a test or a quiz, but it does go through a cyclic merconium intermediate. So essentially what's happening, I have mercury and it's bonded to its 2 acetate groups. And my lone pair, sorry, my pi electrons, not lone pair, are grabbing onto the mercury. We are losing one of those acetate groups. I'm going to draw 2 arrows just so you don't think it's just one step. What's happening then is the mercury is kind of coming back and we're forming that cyclic intermediate. So similar to what we had with our halogenation and halohydro formation, where I have this. So I have that bridged ion intermediate, and then I still have the 2 groups here, and I have 1 group here. I have a positive charge. So water, I know it doesn't look like I have water, but again, you don't have to know the whole mechanism, and some of it isn't even all the way understood, but it's going to attack the more substituted carbon, and then we break this. Eventually, we end up reducing it down to an OH group, but this is how we're getting that anti-stereochemistry, is because I have that cyclic intermediate on top. I end up with my two groups opposite of each other. I know right now one of the groups is mercury bonded to an acetate, but that does come down eventually to that hydroxyl group. I'm sorry, to the hydrogen. Right, so right now we have, right, I have an OH group here. I guess water, I still have that proton on there. I have these two groups. I know I'm not showing stereochemistry very well. This is what happens when I say you don't have to reduce it. I start getting really sloppy on you, or reproduce it. And there's a hydrogen also. So we end up deprotonating that OH group. And then we have a few more steps. We throw in sodium borohydride, and we eventually get down to our product. Actually, let's draw it so it matches a little bit better. I have my OH group down. I have a new hydrogen here. I have a methyl group and a hydrogen, and then those two methyl groups. So again, you don't have to reproduce this. I know it's kind of a mess, but the part that I want you to know is that it's a cyclic intermediate, and that's how it ends up anti. So we do go through this fancy mercury bridged intermediate. So mercury acetate, mercury 2 acetate, sodium borohydride in separate steps. Stereochemistry is anti. It is regiospecific. We want the Markovnikov product. So the OH group, the hydroxyl group, right, because we're adding water, is going on the more substituted of the two carbons. Our last method, C, is hydroboration. Followed by an oxidation step. So hydroboration oxidation. So my alkene, this one's happening in 2 steps also. So BH3, usually we need tetrahydrofuran as a solvent. If you forget the THF, if you're filling in the stuff that goes on the arrow, I'm fine with that. You do need the BH3, however. And then in a second step, hydrogen peroxide, so H2O2, and hydroxide ions. And this one is actually going to give us the non-Markovnikov product. So I'm actually going to end up with the OH group on the less substituted carbon. So it is regiospecific. But we're going to get the non-Markovnikov product. So my hydroxyl group on less, least, same thing, substituted carbon. It is also stereospecific. And we want the hydrogen, again, we are just adding water, so I want the hydrogen and the hydroxyl group to actually be syn to each other, which is the opposite of anti. I want them both up or both down, both out, both back, however you want to draw it, but they need to be on the same, going in the same direction. Oops, sorry about that. So syn stereochemistry. Syn being anti to anti, right? They're going to be on the same instead of opposite. So our mechanism for this one, and this one we're just doing a partial mechanism. We're not going to do the entire thing. So I'm going to take I'm using the same, here, let me just copy it down here so we can see without me scrolling up and down all the time. So this was the reactant, right, the alkene that we started out with. I'm going to kind of flatten it a little bit, so I'm going to draw it kind of weird. I'm going to take those two carbons that have the pi bond, and then I'm just going to kind of draw those guys out of my way. And then I'm going to draw one of the hydrogens on my BH3 out. Sorry, it's BH2 then, because I'm drawing one of them out. Right, BH3 is actually boron bonded to 3 hydrogen. So what I'm doing is I'm just drawing one of those bonds instead of writing BH3 or drawing them all. So this one's going to go through a transition state that is, well, let me just show you. So we're going to have these guys grab on, and then this is going to come back down. And then I'm going to go through kind of a squared off transition state. Remember, transition states is where I have those partially formed and partially broken bonds. So this pi bond is being broken. I'm forming a bond. I just want to draw it neater. I'm forming a bond between that carbon and that boron. I'm forming a bond between this carbon and that hydrogen, and then I'm breaking the bond between that hydrogen and that boron. It is a transition state, so I put brackets and my double dagger symbol. So I get this square transition state where I'm forming both of the bonds at the same time. And by both of the bonds, I mean the bond between the carbon and the hydrogen and the bond between the carbon and the boron. The other thing you want to notice is that the boron is on the less substituted side, the hydrogen's on the more substituted side. Hydrogen's smaller, so it's easier for it to add there. Because those are happening at the same time, it has to be syn. Syn, remember, means they're on the same side. So because I'm forming both of those bonds, right, the bond between carbon and boron and the bond between carbon and hydrogen at the same time, they're on the same side because they're attached to each other when they're forming. So I get syn, and then also the hydrogen goes to the more substituted side, right? It's a steric issue. So that's how we end up with non-Markovnikov. Right? Normally we put the OH group on the more substituted, the hydrogen on the less substituted. This time hydrogen's on the more substituted. That boron group is eventually going to become the hydroxyl group. That's on the less. So non-Markovnikov. So syn, because they're actually bonded to each other as they're both bonding to the molecule, so it has to be on the same side. And then for steric reasons, the hydrogen's on the side of the molecule that has less carbon, right? Less steric hindrance. And then what I have at this point are those two carbons. These are these carbons. Maybe it's easier if I draw them. I have syn, so this is up. This BH2 group is up. One of these is out. One of those is back. So I got this guy. This next part, this is where we're going to end up. I've run out of room, so we're just going to go down here. I know it's weird, but this is where we show in our hydrogen peroxide and our hydroxyl group, and we end up with that group becoming an OH group. So the boron's gone, I have a hydroxyl group instead. And you don't need the mechanism for that part. We are just doing kind of the partial mechanism. So don't need mechanism. So I do want you to know this part up till here. And then that last part where I'm adding the hydrogen peroxide and the hydroxyl group, you don't need to know the mechanism for it. So the 3 ways to add water, just be really careful because our product is an alcohol in all of them, but they're slightly different in terms of stereochemistry and regiochemistry. So going back up here, right, acid catalyzed, I get my Markovnikov product. So my hydroxyl group is going to be on the more substituted carbon. From a stereochemistry standpoint, though, I get both stereoisomers. Oxymercuration, I also get Markovnikov product, the same as acid catalyzed, but I only get anti-stereochemistry. With the hydroboration, I actually get non-Markovnikov products and syn stereochemistry. That one's usually the easier one to recognize because it's the only one that's not Markovnikov. So as an example, you just have to be really careful. Sometimes you can have more than one option for your answer, and sometimes you don't, depending on the stereochemistry of the product that I give you. So if this is my reactant, and then we have to put what's on the line. So if I give us this product first, so I'm going to have my hydroxyl group here. Try to make that so it looks remotely good. So that methyl group isn't involved in my reaction, so nothing happens to that. So I'm going to have my hydroxyl group coming out, which means this methyl group is going back. And then on my other carbon, I'm going to have my methyl group coming out. We also could get as a product again, that's not involved in the reaction, so that one doesn't matter. This time I'm going to have my methyl group coming out and then my hydroxyl group going back. And then on this carbon, I still have my methyl group coming out. So if we have to figure out what goes on the line, right? I have acid catalyzed, so I can use sulfuric acid and water. We have the oxymercuration reagents, and we have the hydroboration reagents. Now, my regiochemistry is the same for both of these, right? So I can't use Markovnikov versus non-Markovnikov to figure out my product because these two carbons are equally substituted. I can't differentiate based on that. So the only thing I have is the stereochemistry. So the hydrogen, right, I didn't draw it, but there is a hydrogen going back here. And then here my hydrogen's also going back because the methyl group's going forward. So on this one, my hydroxyl group and my hydrogen are syn to each other. On this one, my hydroxyl group and my hydrogen are anti to each other. So if I gave you both of those, so if there's like a plus side between them and one arrow, anti and syn, it's going to be the acid catalyzed because that's the one where we get the mixture of stereoisomers. If we only got the first one, it's going to be the oxymercuration. If we only got the second one, it's going to be the hydroboration. Oftentimes, like I said, you can tell based on substitution, but these ones are equally substituted, so just be careful. Let's actually number them. So if this is A and this is B, so if our products are both A and B, then we're using H2SO4 and water, right? That's going to be our answer. If only A is our anti, we're using our mercury 2 acetate and sodium borohydride, right? That's going to be what goes on the arrow. If only B, then we're using our hydroboration oxidation material reagents. So BH3THF. Again, if you forget the THF, that's fine. We do need the 1 and the 2 again. I will take off if you don't forget those numbers there. And hydroxide. So again, just be really careful. We get alcohols are product in all three, but based on regiochemistry, stereochemistry, you can usually differentiate. Sometimes they're both options, just depending on what I give you. So just, again, be really careful. Go through the practice problem.